All right, I'm Andrew. I work on Serenity OS and the Ladybird browser, and I'm going to talk to you about the web here in this C++ talk. Hopefully, you can make this interesting. This is going to be about my journey trying to figure out how we can properly model execution of JavaScript and the process model for the web browser as we're implementing the Ladybird project. So hopefully this tickles some good stuff here. So quick overview. Hopefully this whole slide is a review for everybody in the room, but this is the parts of the native code model for executing C++ programs on Linux or Windows or whatever other operating system for hosted execution that's going to be relevant to the later exploration of what it looks like to do this for a different JavaScript-based execution stuff. So when you start your program, the operating system is going to create a process for you. That process has one or more threads of execution. And the interesting thing about those threads of execution is that they all share the same address space. If the operating system wants to schedule a different thread, it needs to swap in the thread state of a different, it needs to save off the thread state from one thread of execution and put it somewhere, and then load it into the CPU when it wants to actually execute it. And obviously you can have multiple CPUs and whatever else, but generally this includes live registers, which includes your variables, floating point state, stack pointer, page tables, whatever else. The thread local state for each thread of execution lives in one of two places. It's either going to be some global thread state in thread local storage, or it's going to be on the stack. And the stack holds the list of functions that you have and all your function locals, and the TLS has global variables, whatever else. The last piece here that's kind of relevant is that all of your variable names are going to be resolved at compile and link time or at load time, right? If you want to reference some variable, then the compiler has to do something with that variable to store it in the program. And you can only do this at load time for global variables and function names. Like when you launch a program and it needs to find libc, there's going to be a program, the loader, that goes and finds you the definition of printf and whatever else. And the interesting thing here is that all these function local names are going to be allocated to registers. There is runtime variable resolution for dynamic modules. Like if you DL open something, you can DL sim it later. If you load a module in Windows, you'll have to use get proc address to get it later. So this is generally how I'm viewing hosted execution in C++. So if we want to look at what does this look like for the web, the most, well, if you want to do anything on the web, you have to use JavaScript, right? And JavaScript is actually standardized. I'm not sure how familiar this room is with the way that works, but it's standardized by this group called ECMA International. They have a technical committee, TC39, that's been standardizing it since about 1994 or so. They're on like the 15th revision now. It is on GitHub, and the draft is there. And whenever anyone wants to make a change to JavaScript to add something interesting, like currently the most interesting one to me is there's a new time API called Temporal. It's currently in stage 4, I believe. Maybe it's in stage 3. But all these proposals go through stages 0 to 4, where 0 is I'm proposing this, 1 is I've talked to it at a meeting, and 4 is it's been merged into the spec. Where the gate from 3 to 4 is that all of the major engines have implemented this feature, right? So in order for something to actually be part of JavaScript, it needs to be implemented by Safari and Chrome and Firefox, and hopefully some of those other independent engines as well. If you actually go to their GitHub, you'll find that if you find a typo in their spec, they'll just merge it. But if you have some other change where you're like, well, this doesn't really behave right, then they're going to have to bring up your pull request at a meeting and whatever else. And this development flow is, I don't know, I think it's quite modern and makes the C++ platform development flow seem a little bit uncomfortable, especially when you see how quickly some of these proposals get through TC39. But anyway, on to how this actually works. So in my description here, I started with processes and I walked my way down to variable names. I'm going to do the opposite for JavaScript. So this JavaScript specification is really broken up into records and abstract operations. where records is just a list of fields or whatever, some grouping of data, and abstract operations is they describe everything in terms of these algorithms you can implement. And for variable access, they have this concept called environment records. And the important thing about records is that they're not actually required to be visible to code. They're just a spec vehicle for describing how things work. And these environment records describe the accessibility of functions and variables, and every function has its own environment record, and it's going to mirror the AST. An interesting thing about JavaScript compared to C++ is that there is a global object. There is a root environment record where any global variables, any global functions will be defined on this global environment record. And generally this corresponds to the global object, but I didn't make my asterisk visible when I changed the color here, but it doesn't quite work that way for window objects because there's a window proxy and whatever else, but it doesn't matter. And this global object on a web page is the window, and it has your embedder specific properties and whatever else, like the web APIs, or if you're in a Node REPL or something, it'll have your file system APIs and whatever else. And so we have this list of environment records that describe how we access variables, which is completely different from, well, it's not completely different. It's similar to the way that your compiler is going to resolve all these statically, but these have to happen dynamically. Actual execution of the code is modeled by these things called realms and execution contexts, where a realm is a wrapper for the global object that holds the global object and whatever embedder state is, where the embedder is a web page or a REPL or whatever else. And these have there is an execution context stack where whoever is actually running this VM has to pop and push execution contexts to figure out which one of these is actually running at any given time on a specific thread of execution. So how does that work? Well, it happens through agents. And there's also an agent cluster, which we'll get to in a second. But this execution context stack belongs to the agent, where each agent has at most one running execution context. It has an executing thread, which can be shared. And each execution context is associated with a realm. Each realm has a global object, all of its intrinsics and vendor-specific objects. And an agent is essentially a thread. And it's not triple equals a thread, because it's not quite the same. What's the analogy for processes? That's agent clusters. So an agent cluster is a set of agents that can communicate via shared memory and observes the same order of atomic operations. When they put agent clusters into the spec, they were specifically thinking about all of these agents are going to live in the same process. And why don't we just have realms and realm clusters? Well, that's because of the web. Essentially, if you open a pop-up window, you're supposed to be able to access the parent window, which if each window is supposed to be its own realm, they need to communicate with each other. So what does that actually mean? Well, it means your thread of execution in a native process is going to be a thread. In JavaScript, it's going to belong to this agent. Your thread context in a native thread is going to be your CPU registers and your stack pointer or whatever else. But in JavaScript, they have this actual execution context model. Variable resolution happens through these environment records instead of through the compiler, and dynamic imports happen through modules, which isn't covered. So this whole description here is a summary of a markdown file I started writing a while back, trying to wrap my head around how this is supposed to work, because the biggest problem that we had when we were trying to model this is that I didn't have a picture like this that said that, okay, I have an agent with a realm with execution context or whatever else. We just started writing code, and without actually referencing the spec. And the biggest lesson learned from working on Ladybird and Serenity OS is that if there's a spec, read it, because people spend a lot of time on it. And if you can actually implement your code to look exactly like the spec and put comments that reference every single spec section, you're going to have a grand old time, and it'll look a lot cleaner, and it'll be very, very easy for new contributors to come in and say, oh, well, would you look at that? You have a realm object and an execution context, and you have all of these concepts that I just read in the spec, and if I want to add something, it's all there. So Thank you.